We're conducting research on conditions that create or destroy trust in consumer IoT devices as experienced by users with disabilities in particular. In order to do that, we're developing a trust framework using empirical and theoretical methodologies, where the empirical thrust will be based on focus groups that will be guided by universal design and universal design learning. And the theoretical thrust will be based on user journaling that will be interpreted using disability studies and feminist ethics of care. And that framework will be used to develop an app that will automatically read the terms of service and other legal agreements of IoT devices that users are using or considering using and present them to those users in an accessible interface.
So we are working with a number of participants, and already we've received a good amount of survey feedback. We have the focus groups that are set for next week, and then the app is already partially developed. So we've made really a great amount of progress and are very excited about the future of the work and the impact that it can have on the field.
The purpose of this project is to secure IoT devices through power-side channel auditing and also privacy-preserved CNNs. First task is to design a hardware called smart plug. And here is a smart plug that provides power to IoT devices, so smart plug can monitor the real-time power consumption. Then it will do data processing and modeling, especially signal modeling for fault detection. Task 2 is to distribute the CNN model from the IoT device to the cloud, so that the IoT device don't know the model but provide the real-time power consumption data for testing, but the cloud has a model but don't have the real-time data. So they don't have to trust each other, but can collaborate to infer real-time power fault detection.
This research is at the intersection between AI and cyber. On one hand, AI can be used as a tool to secure our cyberspace, and on the other hand, AI itself is a cyber system, so it's subject to cyber attacks. Let me give you a couple of examples from both perspectives. The first work is about DeepMac. It's an attack where the attacker can use a deep neural network to discover the correlation between magnetic sensor data and the apps running on the phone and the corresponding account information. So it's a serious attack. We report this in IEEE PERCOM and receive the Best Paper Award. The second work is about cryptojacking. It's an unauthorized use of computing resources to mine cryptocurrency. It was a #1 malware last year. We developed a new algorithm to detect cryptojacking with accuracy as high as 99%. And we present this result in IEEE Infocom last year. We have also studied the problem of backdoor detection in deep neural networks. A backdoor model behaves normally with the normal inputs, but whenever the attacker injects a trigger into the input, it will activate the backdoor and that leads to misclassifications. So we have designed a new scheme which can accurately detect the backdoor in the deep neural networks. And we're going to present this work in ACM Multimedia this year.